Hello, my students. Welcome to today's lesson. In today's lesson, we're going to prove the second, the third, and the no, the third, the fourth, and the fifth laws of exponents. Okay, so let's do it right away. So the law number three. By the way, the it's not called the law number three. Okay, it's number three for us. It's not that this is the way in which that law is referred to. So that law says the following: when you have a power, this is a power, right? I'm elevating a to the x, so this is already a power. And I elevate that power to another power, a to the x, all of this to the y. What you're going to get out of this is a to the x times y. This is the law that I'm going to demonstrate right now. So let's write demonstration. And before I go into the demonstration, let's review something very simple to understand, but I need you to be aware of this. So suppose, guys, that you have three boxes of candy, and each of these boxes have the same number of candy inside. Let's say four pieces of candy. Four pieces of candy, right? Three boxes, each of which has four pieces of candy. So how many pieces of candy do you have? Well, you have three boxes times four, because that's going to be the individual pieces of candy in each box, and so you're going to get 12 pieces of candy. Now if you have n boxes, each of which having a number of m elements inside, candy or soccer balls or whatever have you, then how many elements do you have? You have n boxes times the number of elements that each box has, so you have nm total elements in all of these boxes, n times m, which is the same as this, but in the abstract way. Okay, keep that in mind because we're gonna use that in a moment. So let's start with the proof, guys. So I'm gonna start by writing this left side of this equation, a to the x raised to the y. Okay, and I'm gonna start by using my definition, my previous definition, right? What does this mean? A raised to a power x, that means a times etc. times a x times. It means the product of this number as many times as I'm told in the exponent. So consider this as a single number, guys. A to the x, consider this as a single unit. So I'm raising this number to the y, and by definition that's going to be equal to a to the x times a to the x times etc. times a to the x. How many times? How many of these am I going to have? I'm going to have y factors all equal to a to the x, y times. Okay, perfect. Let's continue. Then a to the x to the y is going to be equal. I'm going to continue with this side of the equation now. Now, each of these factors, guys, is equal to a to the x, and by definition themselves, they can be written in this expanded version, right? Like this a to the x is by definition a times etc. times a. How many a's, or how many times? X times, or let's say x a's. X a's. This all of this is just a to the x, and then we have a times, so I must write a times, and then once again a to the x, which by definition is a times etc. times a. How many a's do I have in here? I have x a's, and then we have a times, and then we go on in the same fashion, and then times, And then once again, you get the idea, right? So we have x a's in here. Okay, guys. So now this is why I told you the thing about the boxes. Um, looking here, guys. If you consider this as a box, consider this as a box, this is a box, as a box. How many boxes do we have in here? We have y boxes, okay? And a to the x is equal to this, so all of this is a box. This is the second box, which corresponds to this second box, etc. until the last box. Now, so if this is a box, if this is the first box, this is the second box, etc., and this is the last box, how many boxes do I have? I have y boxes according to this. One box, two box, y boxes. So one box, two box, y boxes. So we have y boxes, each of which contains xa's multiplying one another. Can you see? So each of which contains xa's. So if if I can see, guys, all of this line is basically just only a's multiplying one another. A times a times a times a times a, blah blah blah. There are so many a's multiplying one another. And how many a's do I have in total? If I have y boxes and each of which has xa's, then in total, how many a's do I have multiplying one another? I have x times y a's. I need to multiply the number of boxes by the number of a's that each box has, which is x. So I have x, y, a's. X times y, a's, which is all of this. And if I can see, if I have a product of only a's, how many a's? This many number of a's, then this can be written as a to the xy, according to my definition, right? And I'm done, because I have demonstrated that a to the x to the y is equal to a to the xy. And the proof is complete. Okay, let's go to the next law. Law number 4. Law number 4 and 5 are a little simpler. Law number 4, a times b raised to the x is equal to a to the x times b to the x. Demonstration. Okay, I'm gonna start again with the left side of my equation, a times b to the x. And by definition, if I'm raising this number to the x, then what that means is that I have ab times etc. times ab. How many times? How many factors or all equal to ab do I have in here? I have x times, or x ab's. This is one ab, this is two ab's, etc. And I have x of those. Perfect. Now, if you remember, there is a very common mathematical fact that says that the order of the products doesn't affect the result, right? I mean, the order of the factors doesn't affect the result of the product. So 2 times 3 times 4 is equal to 3 times 4 times 2, which is equal to 4 times 2 times 3. I can rearrange the factors in any way I want, and I will always get the same result. So that's what I have in here. I have a times b times a times b times etc. So I may want to rearrange the order of the factors. I'm going to first collect all the a's, a times etc. times a. I'm going to collect all the a's and I'm going to put them first. And then I'm going to collect or leave all the b's to the end, like so. So how many a's do I have and how many b's do I have? Well, if I have x factors all equal to this, to ab, then I must have xa's and xb's. in total, right? So how many a's do I have? I have x a's. And how many b's do I have? I have x b's. Let's continue. So by definition, if I have the product of a, just a's, x number of times, then by definition that's equal to a to the x. All of this is a to the x times all of this, which is b to the x, because it's just pure b's multiplying one another. And how many b's do I have? I have x b's. So I have proven that a times b raised to the x is equal to a to the x times b to the x, and the proof is completed. And finally, the last law, law number 5, which is something similar, but now with the division. A over b to the x is equal to a to the x over b to the x. So let's write the demonstration. A to the b to the x is equal, by definition, to a to the b, I'm sorry, a over b times a over b times etc. times a over b. How many fractions do I have? All equal to ab. I have x fractions, all equal to ab multiplying one another. Okay, perfect. So let's continue. Now I have a string of multiplications of fractions. And how do we multiply fractions? Can you remember, for example, when we have 3/4 times 2 over 5? We just multiply directly the numerators. So it's going to be 3 times 2 over 4 times 5. And if I want, I can get the result. There you go. But this is not necessary. As long as I understand that all of this is equal to the multiplication of the numerators over the multiplication of the denominators. So I'm going to do that in here. All of this in the end will be equal to a times a times a times a times a, all the multiplication of the numerators divided by all the multiplications of the denominators, which are just b's. So a times a times a times a times a over b times b times b times b times b. How many a's do I have in here? How many a's? Well, I'm gonna get rid of this part. This is x times. How many a's do I have? I have x a's. How many b's do I have? I have x b's. And thus, if I have this, the multiplication of x a's, I can write that as a to the x. And the multiplication of x b's, I can write that as b to the x. And I have proven what I wanted to prove, that when a fraction is raised to a power, that's the same as raising the numerator to that power and dividing it over the denominator to that power. And the proof is complete. Okay, let me make a stop, guys. So these are the demonstrations for these 5 laws. You need to understand them very well. You need to be understand how to reproduce them on your own. And now let's go on to some other things. Just gonna make a momentary pause. And finally, guys, some exercises. These type of exercises are gonna appear on the workbook for this particular subtopic. And let's read the instruction. Rewrite the following expressions using the laws of exponents and leave a simplified expression in exponential notation. Do not calculate. I don't want you to calculate the final, let's say the final result. What I mean is this, guys. Let's take a look at the first one. We have 2 to the 3 times 2 to the 6, and according to the first law, we can express this as 2 to the 3 plus 6, which is going to be equal to 2 to the 9. That's all I want you to do. just simplify the original expression and leave the simplified version in exponential notation. I don't want you to calculate this. I don't want you to find how much is 2 to the 9. We're just going to keep this answer. 3 to the 2 times 2 to the 3 times 3 to the 3 times 2 to the 4. Let's reorder the factors first because I can always do that. I'm going to express this as 3 to the 2 times 3 to the 3 times 2 to the 3 times 2 to the 4. And then I'm going to apply the same law. 3 to the 2 times 3 to the 3, that's going to be 3 to the 5. And 2 to the 3 times 2 to the 4, that's going to be 2 to the 7. And I'm going to keep this answer. I don't want you to find out how much is 3 to the 5 nor 2 to the 7. I don't care. This is the answer. This is the simplified version of this. And the same for each one of this. 8 to the 5 over 8 to the 2, that's going to be 8 to the 5 minus 2 according to one of our laws. And this is going to be equal to 8 to the 3. 8 to the 3 times b to the 4 over a times b to the 2. Well, I can separate first. I can dislodge this fraction into the multiplication of two independent fractions, right? In this way, look. It's the same, right? I'm considering this as a multiplication of these two fractions. Understand what I did. And now that I have this separation, just consider this and apply the same rule that we applied here. So this is going to be equal to a to the 3 minus 1, which is going to be equal to a to the 2 times b to the 4 over b to the 2, which is going to be b to the 4 minus 2, which is going to be b to the 2. This is the simplified version. You don't have to go through this in between step, okay? I get it. If you go directly to the final answer, that's cool. This one, according to one of our laws, will be 6 raised to the 2 times 12, which is going to be 6 to the 24. That's it. This one, it looks complex. I'm sorry. 7 to the 3, all of that raised to the 3, all of that raised to the 3. So we can first start by saying this, guys. Consider this as a single number, all of this. So we have, and let's call it circle. Okay, let's just call it circle. We have circle to the 3 to the 3. So we have basically, we can make use of this law. A to the x to the y equals a to the xy. And in this particular example, what I'm calling circle plays the role of the a in here. A to the x to the y. Circle to the 3 to the 3. So according to this rule, I should have circle to the 3 times 3, which is equal to circle to the 9, right? But what is circle? Circle is 7 to the 3. So I might as well substitute back again into what I defined circle. So we have 7 to the 3 to the 9. You see what I did? And now I can use once again the same rule. 7 to the 3 to the 9 is going to be 7 to the 3 times 9, which is 7 to the 21. And this is the final simplified version of 7 to the 3 to the 3 to the 3. It's going to be 7 to the 21. I'm basically applying, in this problem, in this particular problem, I'm basically applying this law twice. And that happens very often. Okay? And yeah, that's going to happen very often. So that's what you're going to have to do in the exercises, guys. There are going to be plenty of exercises in the workbook because I want you to get a lot of practice in the laws of exponents. I want you to have so much practice that you don't think twice and you can go directly from something like this to something like this very quickly or as quickly as possible. Okay, let's stop it right there, guys. Thanks so much for your attention. let me go back with you.